Okay, hi. This is my video number 16. Okay, my last two videos, it seems like upside down. So sorry about that. I just bought a new tools that can hold my camera, but what happened when I set in, it's become upside down. So I'm sorry about that. Hopefully this one is better. Okay, so in this video I'll talk on non-autonomous system. Non-autonomous system. Okay, just recall a little bit on the autonomous system. In the autonomous system, we have dealt with linear system and non-linear system. Okay, so what we have done in that, we investigate the behavior of the trajectories or the phase plane of the given system. All right. So in order to do that, we need a critical point where the critical point is at point 0, 0. If it's not 0, then we can make it 0 by doing some transformation. And then we find the eigenvalue of the given system. Okay, so from there we can investigate further. So for non-autonomous system, basically we develop a few theorem, but we have some theorem that we can relate to the autonomous system. Okay, so what does a non-autonomous system means? Yeah. So in general, we consider the system, right? We consider the system x dot equal to f dx, where in this case we have a vector x, so we have a system basically, yeah, where x is vector x1, a function of t, x2, t, and so on, xn. Okay, this is the unknown vector, and f is defined and continuous, yeah, and f tx, which is so f1 tx and so on, fn tx, where x is a vector, is defined and continuous on region D, yeah? And continuous in the region D. I need that's my pen, yeah. In D, where our D is given as tx such that t in between some number r1 and the norm of x is less than a. So I will define later on what norm is. Okay, so this system, let's call that system, let's call this in this video I call it number 1. Okay, we give it name number 1. So this system we call it non-autonomous because the system depend on f itself is depend on t, yeah, depend on t. For the case autonomous system, the function is not depend on t. For the autonomous system, it depends on T. Okay, so this system 1, 1 is called non-autonomous system because ftx depend on T. And then a solution of that equation number 1, or that system number 1, the solution of 1, not necessarily unique, of 1, we denote as or satisfying x t naught equal to x naught be denoted as x t equal to x t naught x naught. Okay, so means that when we say the solution, means this is the solution of the system, the non-autonomous system. Okay, now let us define the stability of the system. Okay, the definition, let xt t naught x naught, okay, be the solution of 1, satisfying of 1, okay, satisfying we have 1 xt is defined on t naught t infinity, and number 2, the point txt in D, for all t greater than t naught, then xt is said to be stable. Stable if, so we have the word stable, this is for the non-autonomous system. Stable if there exists a gamma positive such that every solution x t naught x naught satisfying 1 and 2, so this is 1, this is 2. When the norm of x1 x naught less than those gamma, and number 2, given epsilon positive, there exists a delta positive where our delta less than gamma, such that the norm x naught minus x1 or x1 minus x naught less than delta, which implies that the difference between x t naught x naught and x t naught x1 less than epsilon for all t naught less than infinity. Okay, so what does this mean? What does this mean? So if you have a solution x naught here that gives a solution to the our system, okay, and we have the neighborhood of delta neighborhood, which is delta neighborhood of our point x naught, all right, and we have epsilon somewhere here, then our trajectory just not goes beyond than epsilon. Okay, so this means our solution is stable if just our trajectory just lie inside the epsilon. If you look at here, this means that the solution, the difference of the solution with any points x1 so less than epsilon. Now if the solution is not stable, then it's called unstable. So which means that for the case of unstable, okay, if the solution is not stable, then we call it unstable. Okay, so which means for the unstable case, the trajectories goes beyond the epsilon. Okay, now I give another definition. Definition. The solution is asymptotically stable. You see, the solution is x t naught x naught is said to be asymptotically stable if it is stable means it satisfies the previous definition, and we have another condition that exists rho positive, where rho less than gamma, all right, such that the difference between those points, or the norm of x1 minus x0, this is less than rho, which implies that the limit as t goes to infinity, x t naught x0 minus xt t naught x1 equal to 0. Yeah. So in other words, for the case of asymptotically stable, all right, so we have a delta neighborhood, then we have epsilon much bigger, then our trajectories will approach the critical point. Yeah, trajectory approach the critical point, and we have to understand this is the solution. This is any points or any function. This is the solution function. Then the difference between those things getting close to the 0. So that we call it as asymptotically stable. Yeah, we have word asymptotically stable. Now let me give you some example, yeah, to make things clear. Example. Now consider this system. Let's say x dot equal to 0. Yeah? The solution for this solution, x, is stable. Why? Because if you take the difference of those using those definition, we have x t naught x naught minus x t naught x1, right? This is equal to x naught minus x1. Okay, for t from minus infinity to infinity. Okay, so it is stable but not asymptotically stable. Yeah, not asymptotically stable, but not asymptotically stable. Now if you look at this, yeah, x equal to 0, x dot equal to 0, x dot equal to 0. So the solution for this is x is equal to just a constant c. Yeah, you just integrate those, then give you some constant. All right. So if you plug in there, so what happened in this case is that we have a x t naught x naught minus x t naught x1, that you have x naught minus x1, and the solution is you have c minus c, which is 0. So in other words, it is not less than delta. So in other words, I would say there is rho. So in other words, there exists no rho that satisfying this condition here. Okay, so that's why in this case it's stable but not asymptotically stable. Okay, another example. So every solution of x dot equal to minus tx is asymptotically stable. Why? Because if we consider this, so what we have, the norm of x t naught x naught minus x t naught x1, this is equal to, okay, now what is the solution for this? I think it's not difficult for you to find the solution for that. You just separate the variable. Okay, separate the variable. So you have x dot is dx dt. So we have, if you bring a x to the left, so you have dx over x. This is equal to is it dt? Yeah, this is equal to minus t. Yeah, so there you have ln x is equal to integrate those things, you got minus t squared over 2 plus some constant c. Okay, so where your x is a some constant e to the minus of t squared over 2. Now if you look at here, yeah, if you look at this, so as t goes to infinity, So this goes to 0. All right, whole thing goes to 0. So when it goes to 0, we have this condition here satisfied. So that's why it's asymptotically stable. So for this case, we have this is equal to x0 minus x1, and exponent of, we have t naught squared minus t squared over 2, the exponent. Then as t goes to infinity, so we have those, those things that goes to 0. So this is asymptotically stable. And if we consider of the other example for the unstable case, for the solution x equal to 0 of the problem x dot equal to x squared. Yeah, this is unstable. This is unstable. So why? Think of what is the solution of that. I think again you can solve this. We have dx over x squared. This is equal to dt, right? Equal to dt. Then you can solve for that. So we have x equal to negative 1 over x is negative 1 over t. So obvious that when t goes to infinity, all right, now then we have the x, our x is given as or we get this x, you got t naught x naught. This is equal to x naught 1 over x naught plus t naught minus 1 over t. Okay, 1 over everything. So you can find the solution. It's from here. You can find the solution. And as t goes to infinity, that part then all good. So we have as t goes to infinity, so we have x is of order 1 over 0. So this is undefined. Okay, so when it's undefined, so we have the system is unstable. Okay, next I will discuss on the stability of the linear system for non-autonomous system, but I think I'll stop here for the moment because the memory problem. Okay, so thank you for that.